making a first framework with 1D elements. It's just one of the simplest framework I'm doing. I make a framework with three beams. So I introduced the 0, 0. I just make a framework in 1 meter length, 90 degrees. Then I start with a new line down here. Be careful that you don't have a point other than the end point of the line. I do make a XY, so in this direction 500, and I go up 100 millimeter like I have it. So that's the one. I do the third line. Okay, so that's my framework I want to calculate. I make a fixed point here. I have a moving support here, and I apply a force here. I go over to pre-post. In the pre-post, I take care that I have all my sketch curves in, and I go over to FEM. Okay, and I have my framework. I just look at it in the normal direction. That's it, what I like to have. I make a 1D mesh like before. I take a C-beam, element size 100 eyelet. Look that this is active merge node, and then I say make a mesh here, here, and here. Okay, I will define a 1D element section, and this time I just take the tube. I have an outer dimension of 60 millimeter. Be careful, the parameter here is the radius, not the diameter. And inner, I take a wall thickness of 5 millimeter. I can have a look at it. It's okay. So it's defined. I make the connection between the mesh and the tube. I make this tube out of aluminium. I look that the mesh, the element is visible, edit display like before. Once I look at it as solids, so you see what's happening in there. It's simplified. It's not really the good modeling of this nodes, but it's a simplification. So I return to visualization of curves to better see these nodes there. Okay, I change to simulation, where I put in my force. I put the force on this node. You see there is just one node to this node. We have both elements connected. Once again I put the force. This time I take a ton, just pushing down or pulling down at this area. Then I define user-defined constraints. I say all fixed in this node. Apply, it's all fixed, and up here at this node, I let free that this thing can move in Z direction. So this I make free, and I let make also rotations about the Y direction. Rotation about the Y direction is free, and the Z is free. Now this must be fixed, and the rotation about Y is free. So now I have it. You see, fixed in X and Y direction, free in Z, rotation around Y will be possible. Okay. Look also at the visualization. No movement, no rotation around here, no rotation. Okay, with this definition it should work. Let's run the solution. I look at the results. I found the displacement. It's quite strange. If you look at this deformation, you see I haven't given free the rotation here, and I see there is a rotation or a flexion. In framework theory, this flexion is not taken in consideration. I go and return and change this, the definition down here. I give free also the rotation about Y. Okay, then before I let run, I say the output request of the forces should be active, and then I get this result. Here the deformation is 0.338 millimeters here, because I have 10%. This is 1 meter. It's exactly this 100 millimeter deformation, and you see you have also flexion on it. But like I said, normally we don't take in consideration the flexion. But I want to show you the beam results, axial forces, and you can read out the actual force on this beam. You get these numbers. Try to calculate manually the forces in this framework. It's taken in consideration that also flexion moments are possible, because you have quite a large structure in sense of beam rigidity. I can change that. I go back and I change in the FEM file this mesh here to a mesh that's based on rod elements. C rod. Okay. no C rod, they can't transfer flexion. Because they can't transfer flexion, I have to reduce the number to 1. Otherwise you have a problem. You have possibly in this connection between one to the other element that the flexion is not transferred, so it's like a spherical joint. So I changed that to remember. I changed to rod, and I changed that I have only one bar. That's what I did. Okay, I go back. Should be okay with calculation. What you find here is that you have two errors. I didn't define an area for this rod element, so I have to be careful. I should give an area that's made in physical property tables. This rod should have an area, simplified, I make 200 square millimeters. Okay, close, try once again to let's solve it. Okay, what no, I didn't make any material. So once again back to FEM, physical properties from this rod, and I have to take this aluminium, it's now in the list. Okay, simulation, solve. Hey, shit. We have no loads. What's happening with the loads? So look what's here with the loads and constraints. They are not attached because there are no nodes or new nodes. You have to reattach it to the real node you have here. To reattach now, it's given active. I make the same with the user defined constraint up here. Okay, and I reattach that to this node. Okay, I try if now this analysis will work, and you see now it's working. I look if there is a message. I have no errors, no warnings, so perhaps I'm happy to have a solution. I look at the displacement, and you see the displacement here, that this position there. I can look at the stresses. I have the stress on the red one, on the blue one, and here the yellow one, that are the stresses, but what we are calculating normally are the axial forces. The axial forces I take from the red one, from the bottom one, and from this one. Now you have these numbers which should be really quite near from what you calculated manually. It's okay. It's a little bit difficult to go to from beams to bars, but in principle possible. That's all for this small framework, this 3-beam framework. That's all.